Here we are. It's the physics video lecture. Physics 105B, video lecture 36. And since we have a quiz coming up, I'm going to start off discussing that. A quiz, did I say quiz? A midterm exam. I'm going to start off discussing that, and then we'll move on into Hamiltonian mechanics. So exam next Wednesday, and it'll be the usual time, so somewhat before 9 to sometime after 10. You all have a generous hour plus to work the problems, and I have a few good problems for us, and I'll just go right through what I'm going to have us know. Okay, so the first is going to be on the variational calculus. And then the next two problems will be small oscillations. Okay, so both of these small oscillations and that, you know, we've done so many different things, but that narrows it down nicely. So as far as the variational calculus goes, let's see what we should know here. And the type of problem I'll give us is based on variation of f of y, y prime, x, dx, x1 to x2 equals 0. So we have some kind of principle with a minimum type of principle or extremal principle. And under these circumstances, we have, first of all, the Euler-Lagrange equations. And for this, if it's a one variable problem, it would be, well, it'll have the same form, one or more variables. So this could be y and y sub I, and so forth. In either case, d over dt partial f y prime squared minus partial f with respect to y equals 0. So if there's more than one variable, y sub I, like that. And yet, y prime is equal to dy dx. So yeah, we have the Euler-Lagrange equations, and the other thing we have is from Euler's second form, if f is not explicitly a function of x here, then sum over df dy sub I prime times y sub I prime minus f is equal to a constant. So continuing this list, and by the way, in Lagrangian mechanics, this was the expression that expressed conservation of energy, the relevant one. And this turned into, and more recently, this turned into our Hamiltonian. We went from Lagrangian to Hamiltonian mechanics. Good, so we have that. Now, in the case, you know, this was I equals 1 to n. So, in the n equals 1 case, you know, essentially what I have up there, then we're looking at df dy prime, y prime minus f equals constant. And in this case, you want to be able to take this to the stage of a quadrature, okay? So suppose you have this and you want to obtain the solution as a quadrature. Then what do? Well, then your y prime is dy dx, so you just manipulate this thing until you can solve for dy dx equals, right? It's going to be a function of y, okay? Equals something, and then you separate variables, and then you would have, you know, just making up something. So we have dy dx equals phi of x and y, or let's just say phi of y, and then dx equals dy over phi of y, and then integrating both sides, and you'd say, well, this is as far as I can get. X minus x0 equals this thing here. And then, of course, the last step, if you're lucky, you can actually do the integral, get y, and then invert and get y of x, or x and y of x, yeah. So yeah, you can invert this and finally get y of x. But yeah, that's the steps, and we've done a number of these, so you want to review this. Okay, good. So that is what I had in store for you. And then the theory of small oscillations. Now that brings all kinds of good stuff together in Lagrangian mechanics. So for the small oscillations, so that would be 2 and 3. I'll just run through what we have. You know, we have a Lagrangian. Let's see. So we have our mechanical system, and we obtain this general form: Aij q qi dot qj dot minus u of q, all variables. And then what we did was we expanded around local minimum of the potential energy, stable equilibrium, right? And so we end up turning this into the small oscillations Lagrangian, which looks like this. And just with a clever choice of letters, right? These aren't specifically just masses, but xi dot xj dot minus a half kij xi xj. And of course, in the one-dimensional case, so sum, well, this is a double sum as well, okay? I and j up to n. So in the one-dimensional case, and this is one you should always recognize, you have a half k x dot squared, you have a half m x dot squared minus a half kx squared. Once you get something in this form, at this point you should recognize it, see it. Okay, its differential equation is just going to give you the cosine, the sinusoidal solution, and omega squared is k over m. Now, in a more general situation, you have to do a little bit of work, first of all, to get this, and then to get its solution. But it's a nice form that is just like the one-dimensional case, just to remind you. Okay. So yeah, in the one-dimensional case, you see a Lagrangian like this, or by the way, you see a Hamiltonian or an energy with the plus sign here, then you should be done. You should recognize that you're done, and you just write down the answer. Okay. This could be written a little cleaner. F sum ij xi xj. Okay. So what about these symbols right here? So the mij are these original ones here, evaluated at the equilibrium point. So remember, the kinetic energy, you just, you're going to have some functions here. You just evaluate them at the equilibrium point because you want constants. So that's very easy to do. The xi is just the qi minus q0i. Okay, that's just the new quantity. Its derivatives are, of course, the same here and here. And the k's are those second derivatives of your original potential evaluated at the equilibrium point. You know, if your system has some built-in mathematical ideal springs, then you just inherit those spring constants. Fundamentally, this is what they mean, right? But if you have something with a labeled K, a spring is labeled K, then you don't, you've already done those. So you want to be able to put together that small oscillations Lagrangian, and in the form where these two matrices are symmetric. If they weren't when you started, you'd know how to make them symmetric. And then, having done all of this, you have the determinant of the matrix minus omega squared m plus k equals 0, where this m is your matrix and this k is your Kij matrix. So you form this determinant, and that characteristic polynomial, sometimes it's best just to leave it. Okay, I'm going to give you a 2x2 problem, give you two 2x2 problems, and so if the characteristic polynomial is written out really clearly, you can often just start looking at that to test it out, make sure your limiting cases make sense. Yeah, but this, okay, good. So that's the program. So we have to be able to do this kind of a construction here. This example is really one of the best. You've got a mass. So this mass, without the pendulum hanging from it, would just be your simple harmonic oscillator. It has a pendulum hanging from it. And there are a number of steps to go from here into these forms. And they can't really be skipped, okay? Because what you're going to find on a problem like this is you get this matrix here, M, it's going to be off diagonal. Okay? Definitely going to be off diagonal, so it has those mixed terms. And your dynamical variables turn out to be the x for the large mass and the angle phi for the pendulum. And say you have an x here and lowercase xy here. Remember, you have that systematic process to construct your coordinates. Okay. So you'd start with a kinetic energy at half m x dot squared plus y dot squared is uppercase and lowercase. Okay, but that can't go into the Lagrangian yet. What you're going to have is this lowercase x is the position of the large mass plus L sine phi. Okay. Capital X dot L cos phi, phi dot, right? And you're going to have something similar for y, and you have to, there's the dot, you have to square that, do the same thing for y, sum them, and eventually you're going to get L of x phi x dot phi dot. So you can see when you take the square of this, you're going to get 2L cos phi capital X dot phi dot. Those are the cross terms. Okay. The evaluation at q sub 0 corresponds to phi being 0 because this thing is then hanging vertically. Okay. So you have a number of steps to take a problem like this into this form and pick off all of the the appropriate things here, put them in the matrices and go ahead and get the derivative. Okay, so yeah, you definitely want to have that process, and that takes us through quite a bit of the whole Lagrangian theory. Very nice one. By the way, same with the potential energy. First of all, half k x squared, that's fine, that's for the spring, but then you have a negative mgl cos phi, or actually, then you have plus mgy, okay, the potential energy of the pendulum there. But this has to be turned into, this one's fine already, but this one has to be turned into negative mgl cos phi. And you're not done here because you're going to have to expand the cosine to get your quadratic forms. Okay. So only when you've done all that can you take the kinetic and the potential and call it the Lagrangian. And then only when you do that extra expansion and stuff and evaluate at the equilibrium position, can you actually call it the small oscillation Lagrangian? Good. Let's see. So yeah, we actually did quite a bit on this, and there's systematic step-by-step process in the theory of small oscillations, and then in this one that I was talking about there. So I think you'll enjoy it. Okay. Okay, good. And let's see. Next lecture before the exam. If you have any questions to me, I can talk about that some more. Okay, let's move on. So we left off talking about Hamiltonian mechanics, and have a really interesting topic today. So more Hamiltonian mechanics. We're going to introduce the phase space. So this is a part of the theory that'll go beyond what we do in Lagrangian mechanics. Remember, up until now, I've shown you techniques that we can get the proper equations of motion, but if we actually want to solve them, it looks like we're just going back to the Euler-Lagrange equations. So the phase space is going to actually be an investigation of the Hamiltonian method with its full 2n dynamical variables. So we're looking at a Hamiltonian system. And we'll just look at the conserved energy. So H, Q1 to Qn P1 to Pn. And we'll compare it first of all to Lagrangian, this Lagrangian system, say, from which this was derived. Okay. So after all, remember, we always have to build the Lagrangian first, then we can get the Hamiltonian. So in Lagrangian mechanics, we have n second order differential equations, n second order equations, and the space of coordinates is referred to as the configuration space. So space of coordinates is called configuration space. And there's nothing fancy about that. If it's three space, Cartesian three space, then that is your configuration space. But let's just make sure we have some examples here first of all. So yeah, we're talking about Lagrangian mechanics now before we move on. So example, the Cartesian plane for projectile motion. Okay, and the solution, that's not projection, projectile. Right, and if we're doing, here, use another color. We're doing projectile motion, then we launch, and there's our trajectory. So this configuration space was just the XY plane. Another example over here, we could have, for plane polar coordinates, it's the space of r and phi, for 0 less than or equal to r to infinity, and 0 less than or equal to phi less than or equal to 2 pi. So then the configuration space is that strip of values. If you were to plot them here, you'd say we go from 0 to 2 pi in the phi axis and the r axis, right? So the configuration would be taking place in that strip there, so to speak. Okay. And by the way, this is a great example because it's got one Cartesian coordinate and one angular coordinate. The configuration space for this, it's also a positive x, 0 to 2 pi in the angle, and some subset. Of course, depending on the energy is bounded, but yeah, it's some subset of a Cartesian axis. Okay. Good. So that's our configuration space, and you can extend those to more coordinates. So what about in Hamiltonian mechanics? Well, we have Hamilton mechanics. Well, we have 2n first order differential equations. 2n first order equations. And this opens up a whole different possibility. So the space now, phase space, is the set of all such 2n component vectors, okay? So Q1 to Qn, P1 to Pn. Okay, so it's a 2n dimensional space. Instead of these, 2n dimensional space. So you can think of it as a 2n Cartesian dimensions, but they came from, we started with the configuration space coordinates, whatever they were, when we, made our way into the Hamiltonian. But you think of it as 2n Cartesian dimensions. So that's what the phase space is. So let's write down Hamilton's equations now. In fact, I'm going to do the simple concrete case first, because there's only one case that you can visualize. Okay. N equals 1 degree of freedom. Okay, we got 2 space, that's the board. N equals 2 degrees of freedom, then 2 times n would be 4, and we can no longer visualize. Nonetheless, we get a lot out of this. Okay. So, the example right away of phase space. So we take n equals 1, and here's our phase space, Q, E. And we have H equals H of Q and P. And we have Q dot is equal to partial H with respect to P. And P dot, these are just Hamilton's equations, negative partial H with respect to Q. Now, what's interesting here, we're just looking at them separately, but we could also imagine putting them together, and we would have d over dt of a vector is equal to, well, if the left side's a vector, the right side must also be a vector. So this is dh, and I'm going to write this explicitly, so it's partial h of q and p with respect to p, right, that's my q dot, and it's partial h of q and p with respect to q. This one gets the minus sign. So yeah, we have a vector here, differential equation expressed as a vector, but what this is a vector field. So the Hamilton equations generate a vector field on this phase space. That is to say, you take any point in this phase space, and then the right side of this equation, this derivative, is a vector. So there's a point there. I could call it Q naught, P naught. I won't do columns, I'll do this way, okay? And then attached to that point is a vector. Just suppose it's going there, just for the sake of argument. On the other hand, what is that arrow there? That's the time derivative of that position in phase space, okay? But what's the time derivative of position is a velocity. So it is a sort of a velocity vector in phase space. That means this arrow is telling us where the trajectory is directed, okay? I had that projectile motion there, so this is going, if you had some more points, in other words, say you had one right here, and that vector is pointed that way, and you had one right there, the vector is pointed that way, you can have your vector field, and if you plot enough of those arrows, it'll show you what the trajectories look like. Okay, this is something we do not remotely have with the Lagrangian system. You have to have the first order differential equation. So let's put this in a couple of words. So the left side is I'm going to put it in scare quotes, a velocity vector, because it's a time derivative of a position, right? QP, that's a position in phase space. And the right side is the equation star. The right side is a vector field. And given an initial position here, you can think of the solution as just something that flows out of that initial condition, and it's referred to as the phase flow. Okay. But I'll get to the phase flow in a little bit, because I want to do a concrete example now, namely the harmonic oscillator. Okay, so our example of what I have up here is going to be the harmonic oscillator. That's one that we can completely understand and see all of its features. Okay, so harmonic oscillator as an example. Yeah, so in this case, we're going to write down, make a nice, useful graph here. Call it Q and P. Okay. And what's the Hamiltonian? Hamiltonian is P squared over 2m plus 1/2 K Q squared. The other ways to write this, or P squared, or in fact, or 1/2m P squared plus, as we factored out, 1/2m mk Q squared. Okay. And we have omega squared K over M. So K is M omega squared. We can also write 1/2m squared plus, let's see, okay. I'll probably keep working with this. This is a form that lends itself to recognizing this as a sum of squares, okay, but okay, we'll stick with this one for the moment. This is just there for good measure. Now, what we have is Q dot is equal to dH/dP, so that's P over M. P dot is minus dH/dQ, of course, is minus KQ. And we know that that is d dt QP is equal to, and the right side of these equations, P over M minus KQ. We want to construct this vector field. Easiest way is just to let K and M be 1. And we'll just take it at a couple of points here. So we're out here on the Q axis, and P is equal to 0, and so the second component, minus K times Q, in other words, it's pointing like this. Okay. If we take a point on the P axis, Q is 0, and we just have P over M. So we have one of these. And so you can do a few of these, and you get this clockwise. It's always going to be clockwise. If you take a point in between here, you take a point in between, and then, in other words, let M and K be 1, then you've got P and Q are equal to each other, and so you're going to get your negative for the Y component, right? Your positive one for the X component. So you actually get a circulation here. And that'll, of course, repeat itself. So if you're further away, and those, by the way, will correspond to larger energies, but you're always going to get this clockwise circulation. And so any vectors over here, they're going to increase with distance over here, and so forth. Okay, going to stop drawing them all at some point. But that's what we have so far. Okay, so that's the right side, and that is the derivative of this point QP. So that really is like a trajectory in phase space that's being indicated by this vector field. So again, right side is a vector field, the left side is a velocity vector. So the solution to the harmonic oscillator, I'll use a different color, would be this kind of thing. Okay. Of course, we know the solution to the harmonic oscillator, so let's go ahead and even write that down. So note the solution. It would be Q is equal to, I'll just use A cos omega t plus phi. Omega is root k over m. And P is mq dot, so it's m omega. In this case, minus m omega A sin m. P plus phi. Yeah, okay. Actually, taking these and squaring them and looking at this thing up here is actually not a bad thing either. Okay, let's continue with this. So we can look at the Hamiltonian in a different way now. Let me check the time. We're not going to do this whole thing today, but this is a good start. Let's take this Hamiltonian again. We'll take that matter either and analyze it a little different. Now we know that we have constant H because this is a conservative system, energy is conserved. So we're going to write this a little different. P squared over 2mh. And I'm going to go ahead and write the square root squared, okay, plus q squared divided by 2h over k square root squared equals 1. So that's just a little manipulation of this equation right here. I divided both sides by h. The reason I'm writing square root squared is because this is apparently the equation of an ellipse. So the phase curves of constant h are ellipses. So once again, QP, I'll draw us an ellipse. Yes, we've seen better ellipses, okay, but that corresponds to a certain energy h. Maybe we should write E in there. We can do that. Write E in here. just to indicate that constant value. But the same thing holds as to what we did right here. This is the phase curve because Q and P of T are solutions to the problem, and they're going to exist on this curve for a given E. For a larger energy, larger one, smaller energy, smaller one. And based on the vector field, it's clear that they are always clockwise. Kind of interesting. So that's the phase portrait, okay, of this system here. They are ellipses. Okay. Phase portrait, ellipse, and there's a whole family of them. They're concentric. They do not overlap. I mean, they do not cross. They do not intersect. That's what I want to say. Ellipses that do not intersect. If they did intersect, and this is generally true, if they did intersect, it would mean that you have a point in phase space. Here, let's just kind of draw a picture here. So in the abstract version, QP, suppose you had two phase curves, okay, and they intersected. Well, that would mean that one initial condition can lead to two different solutions, okay, which will violate uniqueness. So yeah, they do not intersect, and you see in these type of situations they're always clockwise. And what we're going to see when we look at another system is that this is the generic picture of a system with a stable equilibrium. Okay, so this phase portrait here should have drawn a nicer one with these concentric ellipses that are, you know, clockwise motions in phase space. That's your generic stable equilibrium. And maybe I'll leave it at that. That's a good point here. Yeah, that's a good point to stop. So we're going to continue with this. This is a great subject. What I'm going to do next time, you know, I'll remind us of this, and then we'll analyze the pendulum, which we know has a harmonic oscillator in a small angle case, but we'll analyze the pendulum that can actually rotate in the full 360 degrees. And we're going to tie some interesting stuff together that we've been doing recently. Okay, but we'll leave it there for now. See you guys next time.